from the turbulence in the atmosphere. Very quiet sound, of course, but this device can sense that sound, and you end up knowing the optical turbulence. We calibrate it so you can determine the optical turbulence close to the ground. And we've got a couple of tons of batteries and some solar panels. This 30-metre tower we have at most of the sites to look at the characteristics of the atmosphere close to the ground. So a really extensive site testing campaign. And this document, the report that we produced, was about 200 pages thick, and then there were supplementary documents, a huge amount of analysis. And since then, we've written lots of papers about the work we did. All the data is available online for people to look at, that kind of thing. But you know, we selected here to build. This was a picture taken before we started the site testing. We had a ceremony. This, I think this was June 2005 or 2006. It was long enough ago, I can't even remember which year it is. And we set up some equipment on the summit. If you were up in the summit, you know, 5 or 6 years ago, you may have seen this. You know, got our solar panels out at the telescope. The sodars are in these units here. We ran that for a few years. But on the site, we've actually started to do, or we haven't started construction. We've moved some rocks, which is a significant indicator of the readiness of the project. So we had to do a little bit of geotechnical work. We had a bulldozer, a couple of bulldozers up there to put a small road around the site so we could have these drilling machines to do some drill some cores. And so we have moved rocks on the mountain, which is an important point in the project to be. So if you've got binoculars, you can read this. This is a summary of all of the science we think the 30-metre telescope will be used to do. Well, one idea of it. But if you summarise it, there's lots of science that can be done in our solar system, asteroids and stuff, and planetary science, and stuff right out to the distant universe. And lots of exciting science in between, the full range of science. And from all these ideas for different observing programs, you can identify observing programs in each of these areas. You know what types of observations you want to take. You can look at different science areas, collect together the common types of observations that you want to make, and then you can start to define instruments that you want to construct for the telescope. And one instrument will serve several areas of science. It won't do everything. That's why you need a variety of instruments, but you can start to define the instruments that you need. And when you look at the sort of science that will be done with a 30-metre telescope, there's cosmological science, and there's exoplanets, and there's other things in between. An important realization is that you have to use adaptive optics. If you're going to build a big telescope, you need to build adaptive optics. And if you don't know what it is, I will explain again in a minute. But basically, you're correcting for the Earth's atmosphere so that you can reach the, you can see fine details on the sky, reaching the limit that the telescope can achieve, rather than being limited by the effects of the atmosphere. So I've talked about the different sorts of instruments that you can envision using to do different sorts of science. So in 2005 and 2006, there was a call put out to the US and Canadian communities at the time to develop concepts for instruments that we would use to guide the design of the observatory. And the community came back with a whole bunch of different ideas. There's, let's see, optical spectrographs, infrared spectrographs. This is the extreme adaptive optics thing for looking at planets. There's a variety of different sorts of instruments. And we can use these instruments to guide the design of the telescope. And so we're building the telescope to do science. So we have an idea of the science we want to do with the telescope. And from the science, we can derive the stuff the engineers need, the technical requirements. We know what science we want, what observations we want to make. The engineers can start to build a telescope or design a telescope that can do it. And when they have a problem with their design, we can evaluate what impact it has on the science we want the telescope to do. So there's a dialogue between the engineers and the scientists all the time. And I'm one of these guys over this side, and I sit with lots of the engineers here, and we're always debating stuff. But the design of the telescope is very fixed, and we continue to evaluate the type of science we think the telescope will be used for. So that when it's built, it's it's got the most up-to-date instruments, the most relevant instruments for the type of science we think it will be used for. So this is a list of all the instruments that we use in the design, and there was a subset of instruments, these here, which we used, have been selected for first light instruments. So we have a budget, a certain amount of money we can spend on building the telescope, and these three instruments are included in that budget. And then we have a process for developing second generation instruments, which will begin pretty soon actually. But all of these concepts are all sort of not notional, they're concepts, there's no fixed plan for second generation instruments. It will be responsive to what the user community, what scientists want. So all these are future instruments, or possible future instruments. The hardest thing about building the TMT, or any of these big telescopes, is building the primary mirror, controlling the primary mirror. Here you can see it was 492 segments that make up the primary mirror. They're all independent, physically independent segments, but they all have to work as if they're one big mirror. The Keck telescopes have been doing this successfully for 20 years. Before I joined the project, people were already worried about how to do this, and they've been working on it for many, many years. So the design, this is a view of the back side of the mirror, or the support structure. The design of the control system is very advanced. So these are some renderings that made, one of my friends in the office made these for me about a month ago. The most up-to-date renderings we have of the design for the primary mirror. You can see all this complicated structure underneath. But there's a huge amount of prototyping work has been done. So each segment is 1.4 meters across, so nearly my arm span. And each segment sits on 3 of these actuators. These actuators push and pull and tip and tilt the segment, and the position of the segment is measured using these edge sensors. There's a dozen of them around every segment, and you can measure the height difference and the angle between one segment and its neighbours, and then you calculate the appropriate corrections you have to apply to every segment. The corrections are done using these actuators. And behind every segment, you can see in this picture, this is an upside down segment, there's all this complicated structure at the back called a warping harness. So you can bend the glass a little bit as well to do very fine corrections. And this is dynamics testing to see how the system responds to if it's vibrating. This is the industrial plans essentially at the telescope, pumps and compressors and things like that. But the mirror has to be very, very still. So we have to evaluate how well the system will be able to work in the sorts of expected environments on the summit, or on the 13 North side. So we actually are starting to have parts of the telescope made. These are, or some of them, 60 segments have been made over in Japan, and some of these segments are now going off to get polished. So they're round blanks. They'll be polished, and then the sides will be chopped off, and they'll be ready then to start to be processed a bit further and then eventually integrated into the telescope. So that what I like to see here is this is some real part of the telescope. After working on the project for a dozen years, it's nice to see something real happening. So on adaptive optics, I don't know how, and it's a bit dark, I can't see your faces. I don't know how much you know about the tools that astronomers use. It's not really a tool, it's something they have to do, is correct for the Earth's atmosphere. If you look at a star with high magnification, this is what it looks like, dancing around, all pixelated, not pixelated, it's not a nice round star. It's a bit of a mess. You want to correct it. Let me just fast forward. There you go. So if you lay on the bottom of a swimming pool with your goggles on, looking up, that's what the Earth's atmosphere is doing to the starlight as it comes down, distorting it. And adaptive optics, AO, corrects for this distortion. So there you go. This is from a movie made by the Gemini telescope people. That's an 8-meter telescope that's up on the summit here. So it illustrates how adaptive optics works. The light comes down, hits the mirror, up to the secondary mirror, and down. This thing here is where the Gemini telescope has its instruments. And we'll zoom in a minute to one of them, which is the adaptive optics module. So the light comes in, eventually. Should fast forward. It is the light. Okay, so it's coming in. It's going. This is a flexible mirror. You'll see it in a minute. This is a wavefront sensor to detect how the light has been messed up. This is uncorrected images dancing around like the movie I just showed you. Now, when the light comes in, we talk about wavefronts. You'll see these wobbly potato chips, they represent the wavefront of the light, how it's been disturbed by the atmosphere. This wavefront sensor measures those distorted wavefronts. You see this mirror now, it's a deformable mirror. And now the potato chips are flat. It corrects the wavefront and makes it flat again. You watch what happens to the image in a second. Eventually, adaptive optics, it corrects the images for you. So the TMT has been designed from the very beginning to have adaptive optics because it's important for the science we think the telescope will do. And a lot of science uses adaptive optics nowadays. And if you're going to build a big telescope, you'd be crazy to do it without adaptive optics. If a 30-meter telescope, kept telescopes at 10 meters, d to the 4, the diameter to the power 4, the TMT will be 81 times more sensitive than the 10-meter Keck telescopes. So it really helps with the sensitivity. And we have this design for a really fancy adaptive optics system with 2 of those deformable mirrors, one to correct all the turbulence close to the ground, one to correct the turbulence high up in the atmosphere, and it should provide a very good correction across a relatively wide field of view. And it can support up to 3 instruments. And I'll tell you in a bit, 2 of the first light instruments use adaptive optics. One of them is a seeing limited instrument without any atmospheric correction. So we have this big laser system which shoots lasers up into the atmosphere and makes our own laser guide stars at any position in the sky. So this is a system in Chile, the Gemini South Telescope, in fact, with their laser system, multiple guide stars. You can have a galaxy, for example, an extended object, put some laser guide stars around it and get a really good adaptive optics corrected wide field image of science targets. And there's a huge amount of work to develop this adaptive optics system. graphical processing units. We went out and we spent, I think, $20,000 on a fast computer to do all the computation for the adaptive optics system, to do a test bed. And then one of the chaps went to Best Buy and bought a $200 computer. I don't think it's this one. You went and bought a $200 computer using the graphical processing unit, wrote the software that works as well as on the $20,000 computer. So you became a bit famous in the project. And so there's a lot of work being done on adaptive optics. And one thing you get with adaptive optics, this nice imaging, you can do something called astrometry. So this is another tool that astronomers can use. Astrometry is measuring the position of things in space. And I've got this science example here. So this is a distant quasar, and this is a big galaxy with dark matter in it. The dark matter in the galaxy acts as a gravitational lens. So the quasar is re-imaged by us here. It's re-imaged around the lensing object. You can see several images of the quasar. By measuring the position of those images, you can actually work out the dark matter distribution and even variations in the dark matter distribution in these things. So that's some pretty exciting science you can do just by measuring the position of stuff. And I'll give you another example in a while about measuring the position of things and the exciting science you can do. Another tool, spectroscopy. All big telescopes nowadays very rarely take pretty pictures. They nearly always have been used for spectroscopy. So spectroscopy is a tool that astronomers can use to characterize the physical conditions or the composition of an object. Here's a cloud of gas emitting light down here, so that the unique signature of the components in the gas, you can identify what the gas is made from by its spectrum, or absorption lines as well. There's a hot black body or hot body causes absorption in the spectrum as it passes through the gas, and you hit an absorption spectrum. You know what materials are there. You can tell how hot the material is, how fast it's moving around, that kind of thing. So if you have a big cloud of gas or a galaxy that's moving away from us fast, this would be the spectrum. If the object were at rest, if it's moving away from us fast, it's redshifted. You can see a shift along the wavelengths. You can do a lot of science using spectroscopy. So here's an example of science you can do, measuring the position of things. This is a simulation. This is the Keck telescope at the moment, looking at the galactic center, making a movie of images taken probably once every 6 months or so. You can see the stars moving around a supermassive black hole in the galactic center. With TNT, you can see lots more stars, and you can measure their positions much more accurately. So the kind of science you can do, these stars are moving in elliptical orbits. So those elliptical orbits precess due to as it predicted by general relativity. So you can test general relativity and the distribution of dark matter in the center of the galaxy, that kind of thing. Even star formation in this extreme environment is a big area of study. And one capability that this instrument has, this IRIS, one of the first light instruments that sits under the adaptive optics system, it has something called an integral field unit, and that allows you to do spectroscopy of, well, I'll explain what an integral field unit does in a minute. So thinking of the imaging, I'll show you that simulation of the stars in the galactic center. That would all be happening in the very center of this field of this image here. That first light instrument, IRIS, the infrared imaging spectrograph, has an imaging channel which is 17 arc seconds on a side, 16.4 I think, given the detectors that are available at the moment. And this is a simulation of what the The stars look very, very nice right to the very edge of the field. So using adaptive optics, you can correct for quite a big field of view. Now, I've talked about this other capability this instrument has. And a few minutes ago, I told you about spectroscopy. So, the IRIS instrument has an imaging channel and an integral field unit, or an integral field spectrograph. So you imagine a two-dimensional image, here we are, two-dimensional image, and every pixel in the image, you get a spectrum in this direction. So you end up with what's called a data cube, X and Y, and wavelength in the other direction. And you can slice and dice your data to do all sorts of investigations of characterization of the objects you want to look at. So this is what the instrument looks like. It would probably just about fit in this room, wouldn't it? Over 4 meters tall. So it's a big instrument. And that is just one instrument that hangs underneath the adaptive optics system, which would fill most of the front of this lecture theatre. And here's the imaging channel, and this is the integral field unit channel on that side. And people are building prototypes of some of this hardware. This is all cold in here, liquid nitrogen temperature. And it's difficult to make mechanisms that move accurately in those conditions. So that they've built prototypes to show that they can do it. And there's other parts of the system as well which have to move incredibly accurately in cold temperatures. And it's not easy to do. So there's been a lot of prototyping work to prove that these things can be made. So a science area that TMT can contribute to. Dark matter. Dark matter pervades the universe, and the evolution of the universe is fundamentally linked to the characteristics and the distribution of dark matter. So this is a simulation of the evolution of the universe. You can see the spongy texture. Each dot is a galaxy or a supercluster of galaxies. You can see how the universe has evolved over time. And that evolution, these models, change the properties of dark matter a little bit. It drastically changes the outcome of these models. So we can study the evolution of the universe. You look at distant things, you're looking a long way back in time. So I know I've just copied different ages here, but this is supposed to be, we're on this side, and over here is a distant quasar. And the light from that quasar passes through the universe. This is the olden days, up to us here, now in the present. And that light from the quasar is imprinted with absorption features. It passes through hydrogen gas. And where it passes through a dense bit of hydrogen gas, there's an absorption feature. And that hydrogen gas is moving at a certain speed from us due to the expansion of the universe. So here, along the pencil beam, we can measure the amount and the position of material along pencil beam from our telescope. So at the moment we are limited to using bright quasars, which are about, I'm not sure how old a quasar is, about 10 billion years old, something like that, the oldest. And that means we can only see a certain way back in time into the universe. But with the TMT, because it's a big mirror and the adaptive optics for the high sensitivity, we can look at much fainter sources, which are very early galaxies which started to form. We can look at the light from those and see how it's been imprinted with these absorption lines. And we can look at lots more of them. So, and they're further away than quasars. So we can do much stronger tests of universal evolution, as it were, evolution of the universe. So another instrument I want to tell you about is the infrared multi-object spectrograph, which sits on top of the adaptive optics system. And the Keck telescopes, about 18 months ago, this system was delivered, the MOSFire system. It was built at Caltech, and it's a really versatile system. It's a multi-object spectrograph. You can do infrared spectra of a whole bunch of up to 46 different objects. But it's used for looking at very distant quasars and galaxies, galactic evolution. It's used for exoplanet science. For some reason astronomers have found ways to use it for all sorts of things it wasn't envisioned to be used for. Very powerful instrument. So you have a field with a bunch of objects in, and you can take spectra of those objects because of this device here. If you want to take a spectrum of an object, you have to put the object over a slit. The light comes through the slit into a grating, a diffraction grating, and disperses it into its colours. Here there's a mechanism for making 46 different slits at different positions. And this is all coal inside the dewar, inside the big thermos flask, which is the instrument. So this is coal, and it can be reconfigured quickly, and you can do lots of spectra very efficiently with this system. Now, there's this third instrument as well as a first light instrument, the wide field optical spectrograph, and it's big. Here's an image to show how big it is. This is a very old image in the design. These big wheels, they rotate as the field rotates, as the Earth turns. So this whole system moves around these wheels. They're 4 meters across, these wheels are. So this is a really big system. And this is a more recent image. There's a robotic mask exchanger for you can do multi-object spectroscopy with it, but you have to have a big sheet of metal with little slits in it, cut into it, and this robot exchanger will put the mask in the system. Your stars or galaxies or whatever the ones you're interested in, the light will fall onto the slits, and then you can do your spectroscopy with it. And we understand pretty well what this is supposed to look like. The people over at Manoa are working on the detectors. The camera system's been done in Japan. I'm trying to think what the distribution of work is to build this instrument. It's a $60 million instrument, and the work's been shared amongst all the different sorts of partners in the project. Other science the telescope was designed to do is extreme adaptive optics. If you've seen pictures that look like this, where this mess in the middle is the leftover light from a star, and there's planets orbiting this star. We've done our best to block out the light from the star, so we can see the faint planets going around it. In fact, the last couple of days I was up at the Subaru telescope. This is what they were doing: extreme adaptive optics. It's incredible. So, to support this kind of science, the primary mirror has to be as circular as possible. The gaps between the segments have to be small, and the surface figure has to meet very tight requirements, and you have to have a very simple top end to your telescope. So those are design features to support that kind of science. There isn't an instrument planned in the budget for that, but we expect one of the second generation instruments to be like that, so the telescope can support it. Let me just go back. If an example of type of measurement you might want to do. Here's an exoplanet host star. Here's the planet that orbits around it. When that planet passes in front of the host star, some of the light passes through the atmosphere of the planet. And with very careful measurements, when the planet's not in front of the star and when it is, you can deduce the composition of the atmosphere. People have just started to do this actually with that Mossfire instrument I'll show you at Kent, but it's very, very difficult, because it should be relatively easy with TMT to do it for lots and lots of different stars. And the kind of observations you need for one type of observation you can use to do that type of science is high resolution spectroscopy, and by having the instruments on these platforms at the side, gravity is always pointing down, and you don't have to move the instruments around. The spectrographs can be very stable, which is a useful thing. And I've got a science example here. This is called the Rossiter-McLaughlin effect. If you have an exoplanet host star, and the planet is coming around, transiting in front of the star, you can measure the velocity of that star. You know, the stars wobble and the planets go around them. So this is the wobble of the planet. If you zoom in on the area when this is the velocity of the host star, sorry. If you zoom in on the area where the planet is going in front of the star, there's an imprint, a signature caused by the planet blocking off first the light of the star that's approaching you, and then of it receding. And you can do a whole bunch of characterization of the exoplanet system using these types of observations. And you can just about do that with some of the telescopes now, but it's very difficult, and you can only do it for less than a handful, like 3 or 4 different objects. But with TMT, it should become quite routine. So you can look at hundreds of objects and really do some proper statistics and learn about the full range of objects that are out there. So, TMT, I've talked about the science, how we're going to do it, and this is the schedule. 2014, here we are at the moment. We expected 6 months ago, in April this month, that we would move into the construction phase. And we'd start to see some activity on the site. We could place contracts for building the enclosure and that kind of thing. There's a little bit of a delay, but we should really move into this construction phase in the next about 6 weeks' time. And we're in a good position to build. We've got, I showed you, we've moved some rocks on the mountain. So we have, well, the University of Hawaii has a building permit, and we're about to, hopefully, the land board will give the green light or the rubber stamp to our lease with the University of Hawaii. Right at the start of the talk, I was talking about the design of the telescope, and it's all very well understood. We know what we want to build, and we expect it really to kick off at the moment. I can even tell you that in the present schedule, you can be very exact, and the 16th of April 2024 is when the present schedule says we'll start science operations. Of course, there's some reality will change that date somewhat. And then the price tag in dollars backdated a couple of years is well over $1 billion. So it's a really big project, but this big international partnership. And this is, in a few weeks' time, this is locally the next big stage is the land board, fingers crossed, saying that the lease with the University of Hawaii is acceptable. So I hope you can see that the TMT can do some, or should be able to do some amazing science. We think we understand how to build it. We're on the brink of really starting to see this telescope start to take shape up on the mountain. And it's an exciting time. So I'll stop there and take any questions. Thank you.
Any questions?
You had down very fast.
Why 30 meters? Why not 42.3 or 2036?
Well, many years ago, probably before I joined the project, people figured out they thought 30 meters is technologically feasible, financially feasible, and scientifically justifiable. It's the next logical step to take in telescope design, because we can do it. And the design for, or the scope for the 30-meter telescope project has been very fixed for many years. Do you remember about the OWL project about 15 years ago, the European 100-meter project? that shrunk to 50 metres, shrunk to 42, and is now 39. So 39 and 30, they're pretty similar. What's happened is they've come to the same conclusion that a 30-metre class telescope is technologically feasible and affordable. So that's the answer, I hope.
Yeah, when you hear people talk about site selection, it usually comes down to Chile and the Big Island of Hawaii, and you hear all these different parameters like seeing and accessibility and blah 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 and all this. But what you never hear about is whether they wanted the telescope to be in the northern hemisphere or the southern hemisphere. Does that ever come into consideration, or did that come in with this
It was
telescope?
considered. So the potential science that the telescope can do was assessed and found to be hemisphere independent. You can think of the Magellanic Clouds. They're visible in the south, not from here. That's just one. That's kind of the only thing people can think of that differentiate the northern and the southern hemisphere. It basically doesn't matter which hemisphere you're in. But then there were decisions like, say, the LSST, the Large Synoptic Survey Telescope, is going to be built in Chile. So people said, well, shouldn't next big telescope be built next to it? And so you think about that, and then the overlap of the sky from the two telescopes, from TMT here and LSST down there, is 75% of the sky is overlap. So again, that's not a big discriminator. So scientifically, there's no difference really. Yeah.
You said that the primary mirror was going to be very fast. I was wondering what kind of aberrations you were expecting, if they're going to be really severe or not.
You're looking at the wrong person to answer that, I'm afraid. I'm not an optics person, I'm afraid, so I don't know how to answer your question. Yeah.
The European telescope that's going to be built in Chile, what is the timetable on that?
It's not as exact as the 16th of April 2020. As far I had a look at
At noon.
as far as I can tell, the best public document that talks about the schedule, and they just say the early 2020s, and the GMT, the John Magellan Telescope, says the early 2020s, and my completely unbiased opinion is that the TMT schedule is very mature, and the schedules for the other telescopes aren't as mature, and so that they're more vague, and schedules only ever get longer, unfortunately. So, I think that the TMT is going to be the first big telescope on the sky as well. Any other questions? Oh, there's more. You in the yellow shirt?
I was very curious, how much do each of the segments cost?
The glass itself, I'm trying to think. I have heard people talk about this, but again, I just sit or drink cups of coffee surrounded by the people that know this cost, so I don't take in too much information. I'm trying to think. It's a few. The glass itself ends up, those blanks are a few tens of thousands each. And then the surface figuring, again, is a few tens of thousands. Once you start to put the stuff on the back, a glass segment with sensors and warping harness and most of the structure is about $1 million. So it ends up being a really big fraction of the cost of the telescope, the primary mirror. But the glass itself isn't so huge. It's few tens of thousands of dollars, but I don't know the exact number again, I'm afraid. Yeah.
What are the advantages of having a dome designed like that as opposed to the classical size?
This you can't see this Colop design is the most compact, because it's essentially a sphere. It's the most compact design you can possibly have. So advantages are it's compact, uses less steel, it's cheaper. It's air conditioning. You have to air condition the dome. The smaller the dome, the the less the air conditioning costs. So there's lots of operational advantages. But it's a big project. They had some very traditional sorts of designs. Some that look like the Subaru telescope, like a tin can with doors open, and they were absolutely huge. You know, you could fit several football fields in them and things like that. This is really compact. In fact, it's so compact, we have to, around the aperture, around the hole, we have to put flaps that open up to direct the wind away from the telescope inside, because it's so small. You have to sort of, you know, aerodynamically enlarge it when the telescope's in operation. Any other questions? Yeah.
Once the telescope's finished, who's going to use it? Like, do you already have some kind of line for it?
So the present model is that each partner, of which the University of California, Caltech, Canada, China, and each partner will get a share of the telescope time relative to how much money they put into the project, basically, or how much the value of subsystems that they've delivered. And UH as well gets a fraction of the time. And then pick apart India, for example. India will have about 11, 12, 13% of the time, something like that. And they'll have an allocation committee that you apply to, and they will distribute the time to Indian astronomers using some.
And Hawaii. And our
University of Hawaii would have a TAC, Telescope Allocation Committee, that people here would apply to, and then their time would be divided out. And then there's ideas about having super TACs. If you have two groups of astronomers from different partners, you know, Canadians and Chinese, they want to do the same thing. It's not. It's efficient. It's logical to get those scientists working together, and perhaps allocate a little bit more time than just one application, but not two separate applications. There was another hand. Oh yeah.
Is it possible for a non-partner to buy telescope time?
Yeah. There's a scheme where if you're a 10% partner, you're an official partner. You have someone that sits on the board. You have to put in a certain amount of capital cost money and running costs, that sort of thing. Then you can give that time out to your user community. If you can be a 5% partner, which means you only have to give cash to be a 5% partner. If you're a 10% partner, you have to provide instruments and this sort of thing, and that's how you essentially pay for your time. If you're less than a 5% partner, you have to partner in with another partner, as it were, and somehow form an arrangement. So you could have scenarios where I don't know, a country or a university can have a fairly small slice of the time. It's conceivable, but I'm not sure how the board have figured all that out at the moment. People talk about that sort of thing. Yeah?
As technology becomes more advanced and they're able to make these instruments more compact, will you guys be able to adapt all the instruments and devices on the telescope? Because some of them are really big. And I was wondering if you're able to adapt the telescope and everything to the newer technology, change things out, you know, still be able to work the telescope with newer technology.
The answer is yes and no. Some things, like that big optical spectrograph, the size is dictated by physics, not by technology. So some types of instruments you can't change. If you want to do a certain thing, there has to be a certain size. Now there are new technologies that are coming about that essentially decouple the instrument from the telescope, and then you can build quite compact instruments, and they're getting more and more compact as technologies go on. Just up the street at the Subaru telescope, they're developing something called SCEX-AO, Subaru Chronographic Extreme Adaptive Optics. What that is a very compact adaptive optics system that can feed different instruments, and they have instruments that go on the 8-meter telescope. An 8-meter telescope, you'd think the instruments would be at least as big as this, but they're as big as a shoebox, because it decouples the size of the instrument from the telescope. So the answer is yes and no. Any others? Yeah.
So, do you plan to operate it from the summit or remotely?
Remotely will be steady state operations, and even very remotely, you're probably familiar with, say, Keck has I always keep pointing, I think Keck's in that, the Waimea is in that direction somewhere, I don't know. At the Keck telescope they have control rooms in Waimea, and they just have one person on each telescope and a sort of supervisor up there at night time. And then the astronomers sit at Waimea, and you can, there's a remote control room at Caltech. I've sat in there numerous occasions, and the control room somewhere up in Northern California somewhere. So for TMT, the plan eventually is that there'll be control rooms in Hilo and remote control rooms in all of the partners. That way, a Chinese astronomer doesn't have to get a visa to go observing. You just go to some control room in Beijing or somewhere and observe with TMT. So very remote observing. Initially, it's all going to, the action's all going to be at the summit, you know, when we start to do commissioning and that sort of thing. So it's the way things evolve. All the work's there first, and eventually migrates down to where the air's a bit nicer. Any other? Oh, yeah. Any other questions? Oh, I was going to say come down and get the free stuff, but I'll retract that. And what were you in the back again?
Sorry, just.
Oh, sorry. I was just going to ask, are there any issues powering the observatory?
Yes, there are. The present infrastructure will not support TMT. So TMT is paying for new power cables to be put all up to the summit, which will, they're just paying for an upgrade for the whole mountain. But as far as I'm aware, you can get all the power to TMT through a 4-inch conduit, you know, if you use high voltage and things. So it's not a big, you know, physically a big upgrade, but you know, we have to dig some channels and put these conduits here and stuff. So you do have to upgrade the power supply to the mountain, basically.
4 inches of metal times that distance is still quite a bit.
It is, yeah.
Even just like the price of copper.
True.
Yes, compared to the entire project.
Yeah, I'm not sure what the cost is. I assume Helco will just see this when the construction phase starts, we'll have contracts with Helco for upgrading I remember seeing, because one of the first things we have to do is make the road nice out to the site, and so you make the road nice, and we're going to tarmac it. Is that the right word in America? Tarmac it, put asphalt on it. That's to keep the dust down and stop environmental impact at the sides of the road. So it's going to be tarmac, but the electricity has to be laid pretty early on in the project, the electrical lines. So I've seen that in the plans. Oh yeah.
How many people currently work on the TMT project?
In the project office in Pasadena, there's about 30. It's a very distributed project though. In Canada, there's about, I don't know, half a dozen, something like that. In Tucson, there's a few people. Then there's people at all the partners. And then I can only guess at the number of people that are working in, because like I say, the Melco company, the ones that are building the telescope structure, have got dozens of people working on it, but they're a contractor, as it were, paid to deliver. China, there's tons of work coming out of China. So I've no idea how many people are working on it, I'm afraid. people on the TNT payroll was probably about 40 at the moment. Okay, now you can come down and get the free stuff. Okay, thanks very much.
Yeah.